Thank you.
The floor is yours.
So I think mic working? Okay. Very apt for the last day. I'm going to talk about what happens at the end. So what happens at the end of the lifetime of the objects? What time happens at the end of the lifetime of the actors? Garbage collection in Pony. So I'm going to talk about two protocols. The one is called ORCA, and it is about garbage collection for the objects. And I will discuss the protocol, some benchmarks, message delivery, and of course some interesting bits about the proof. And then I'm going to talk about termination. When does a program terminate, which leads me to garbage collection of actors, and again, the protocol and the proof. So the first question is, does garbage collection matter? After all, if you are perhaps an atheist, after the object is no longer there, we don't care. So that was my view of things a couple of years ago, that garbage collection was a little part I was not very interested in. But I was wrong. For instance, I have been told that at some financial institutions, when there is too much pressure on the system, they turn garbage collection off in order to avoid making the system unresponsive. And 2 years ago also, at summer school also in Bertinoro, Doug Lee was saying that one of the problems in getting good performance and consistent performance out of the system is garbage collection. So what about the Pony garbage collection? So the great advantage of the Pony garbage collection is it is fully concurrent. It is executed by each of the actors, and the actors can execute garbage collection without any form of synchronization with each other. They don't need to send messages. They don't need to have barriers. They don't need to stop the world. They don't need to lock. They don't need to know about each other. And this is what this diagram is showing. Here I have got 3 actors, A, B, C. The colored bits are the parts where they're executing their behaviors, and the gray bit is when an actor is doing garbage collection. So you can see that at this point, 3 of them are doing garbage collection each other. So this is the picture in theory. This is a benchmark that Juliana devised recently. And you can see what each of the core is doing at a certain time. So she has added telemetrics to the system. So we can see when an actor is doing yellow stuff, then he's executing the behavior. When he's doing red stuff, he's doing what is needed in order to send messages. The green stuff is what is needed when you receive a message, and GC is a cycle where he goes through his heap and he tries to find what he can remove. And we see that the things happen in a fully concurrent manner. So here there is a little zoom in into that part, and you can see this actor is sending and receiving. This one is just garbage collecting. This is doing behavior, receive, behavior, garbage collect, and so on. Okay, so what are the challenges when we have a concurrent system and we want to collect, we want to do garbage collection? The first one is, who should be doing the collecting? Where does it happen? Who does it? The other one is, how do we avoid data races between the garbage collection and the mutation, between the garbage collection phase and the behavior of the actors? After all, they both go through the heap and they search for stuff. So how do we make sure they don't tread on each other's toes? So the answer to the first one is, we already saw it. It is another actor, and in the particular case, it is the actor who allocated the object. So if you allocate an object, you are also responsible for removing it when it's no longer reachable by anybody. And we call the allocating actor the owner, but this has nothing to do with ownership types. It is not a restriction on the hierarchy of objects. Sorry, it's not a restriction on the topology of objects in the heap. It is just some actor, a relation where every object has got an owner, the actor who allocated it, and that's it. How do we avoid data races between garbage collection and mutators? Well, we said it already, we use the type system. The type system has got enough information when we compile the program, and the garbage collector will be using that information in order not to get into races. The third challenge is, but then, since the owner is responsible for removing the object, how does the owner know when it's time to remove the object? How does the owner know that there are no reference to the particular object? And the answer is we are using deferred reference counts, and we are also using the messaging mechanism in order to keep track of the number of other actors who have got some interest in the current object. And the last one is, how do we deal with uncertainty in message delivery? We said that the semantics is non-deterministic with respect to when does a message arrive at the queue, when does it get taken from the queue. But it's not totally non-deterministic because we have a causal message delivery, and this is crucial for the protocol. So there is a tight connection between the language and the runtime system design. And as I said yesterday, the garbage collector existed before the programming language existed, but the programming language provided the things that were necessary for the garbage collection. So here is the ORCA protocol. So I said that the type system gives enough guarantees in order to make garbage collection safe. So what are these type system guarantees? There is the first one is the one that we saw yesterday, which says there are no data races. So again, if in a certain configuration some actor thinks that they can write in an object, and another actor thinks that they can see an object, so they have got a path to that object with a certain capability kappa, and they are not the same actor, then the second actor can only see it as tag. So if somebody can write into an object, other people can use the identity of the object, but they cannot go inside the object, and they cannot do anything much with that object. So that's the first guarantee. And now we have got a second guarantee, which is useful. It's not totally necessary, but it makes the protocol faster. And it says that if I have a path that allows me to reach a point and then go one step further, read the field, and I have a capability kappa. What I meant is the shorter path also has got some capability, so it should be read like this. The shorter path has also got a capability, so I'm not getting capabilities out of thin air. And now, what do we require from the runtime system? We said that we are using deferred reference count. So every actor, and the actors from now on will be called alpha, they keep a reference count table, and in that they assign a number to all the local objects or the objects they own, which they have sent out at some point in the past. If I send it out, what it means is some other actor will have access to that object, and as long as they have access to that object, I'm not allowed to remove it. And also, they keep a reference count for all the foreign objects, all the objects that they have received from an actor, from another actor, from the owner or some other actor. So the reference count table is about what objects do I need to keep alive? This is for my local objects, and which foreign objects I'm interested in, and I don't want to allow the owner to remove them until I tell the owner that they may do so. So we're using the notation alpha reference count O to talk about the contents of the reference count table at alpha for the object O. And when I say O, I mean object or actor. When I say alpha, it is definitely an actor. So there is now an invariant that governs, that is very fundamental to the working of ORCA. And it says that the reference count at the owner of an object has to be greater than 0 under certain condition if either there is some actor, alpha, that can reach the object O, that has got a path to that object with certain capability, either tag or ref or val or whatever. So if some other actor that is not the owner is interested in the object, then the owner must have a reference count greater than 0. And also, if the object is in any queue of any actor, also the owner must have a reference count greater than 0. And this is a wonderful guarantee because with this guarantee, the actor can do garbage collection without consulting any other actor. So here is a possible runtime configuration. I have got 3 actors, alpha 1, alpha 2, alpha 3. I'm only interested in the objects that are owned by alpha 2. So the boxes are talking of ownership. If you know me in some other life, I have worked in ownership types. And then we're also using boxes to indicate ownership, but this is not ownership types ownership. This is garbage collection ownership, as we said. It is the actor who allocated the object. So alpha 2 owns all these objects here. He has got a field that points to object 1 with a reference capability. Object 1 points to object 2 with an ISO capability. Object 2 points to something in another actor and with a reference capability. There is an object here from this actor that has a reference capability pointer to 3, and so on and so on. So this is a possible runtime configuration. And also, alpha 1 has got in his queue a message that contains a pointer to the object 7. So for this possible runtime configuration, we want to consider what does the invariant require. So first is the question, which are the objects that the left-hand side of the implication is talking about? Which are the objects that either another actor has got a path to for the actor alpha 2, or they are in some queue, and we want to have that we are only interested in objects that are owned by alpha 2. So we are only interested in those objects, and for these objects we want to think what are the objects that other actors have got a path and are therefore interested, and which objects are accessible from messages. So the answer is the objects 3 and 5, because this actor has got a path that would allow him to go and access 3 and access 5 as well. And 7 is also of interest because there is this message that is awaiting to be received by alpha 1. So alpha 1 will be reading 7 at some point, or could be reading 7 at some point in the future. And moreover, alpha 2 is one of those alpha 2 needs to be kept alive because all his objects are kept alive. So we are thinking that every object has got a tag reference, an implicit tag reference to his owner, in order to make sure that when an object is around, his actor needs to stay around as well, because they are responsible for removing it if ever they should become unreachable. So these are the objects that the left-hand side is talking about, and here is a possible reference count table which would give positive numbers to those objects. Of course, it could contain more stuff, but that is what is necessary for invariant 2. So now let's look at the same situation and what would garbage collection do. Again, we remember what invariance 2 says. So the and the reference count table is given there. So the first pass, the first stage in garbage collection is we mark all the objects as unreachable. All the objects that we have interest in, we assume that they are unreachable. Then we find all the objects that are reachable from the current actor, and we mark them as R. So the current actor is alpha 2. And then we go and navigate from alpha 2 and and we stop here. We don't get to further than 4 because the path that got me to 4 finishes with a tag reference, so the other objects are not reachable. And for the same reason, we don't get further than 3 because the path to 3 stops with tag, and after that we cannot read anymore. Then we mark as reachable all the objects that have got a reference count greater than 0. So this is 3, this is 5, this is 7, and this is the actor himself. Now, so now all those objects have been marked as reachable, and one has still the old mark as unreachable. So now all the local objects that are marked with U, they can be collected. And they can be collected because of this invariant. The objects that are marked with U, if they are local, we know that they don't have a reference count greater than 0, and we know that the current actor has got no path. If they don't have a reference count greater than 0, then we know that there is no other actor that has got interest in the object, and there is no other actor that contains the object in their queue. Yes?
From where is object 6, sorry, 7? Yeah, no? Object 6 reachable? Or
Object 6 is not reachable.
7, sorry, 7, yeah.
Object 7 is reachable from the message,
Okay.
from there.
Okay.
Thank you for asking. Yes?
Maybe I'm misreading this diagram. Why isn't object 6 reachable? There's a pointer from object 4 to object 6.
Yes, there is a pointer from object 4 to object 6, but we start from alpha 2. So when we start from alpha 2 and we reach this object will say, I'm interested in the identity of that one, but I'm not going to read inside that one. Yeah? So the reachability says there is a path, and the path stops here. It doesn't go any further because if you remember yesterday, we said that viewpoint adaptation means a tag combined with something is undefined.
And then on the other hand, when you have 5 on the left-hand side, that's reachable because there's a reference.
Exactly. Thank you very much. Yes, it is not this path that makes it reachable, it is this path that makes it reachable. So this was exactly why I made the diagram this way. And thank you for asking, because now I have got the opportunity to clarify it. Yeah. So these ones, they were not marked because of reachability. They were marked because the reference count was positive. So the reference count makes the part where we mark as reachable all local objects with a reference count greater than 0 means whatever other actors are interested in, I'm going to protect. Whereas the phase 2 says whatever I can reach, I'm going to protect. And by the time we reach 4, we know that those that are marked as R have got a reference count 0 if they are local, and they are not reachable from the current actor. So for instance, 1 and 2, they don't have reference counts. No other actor is interested in them, but alpha 2 is interested in them, so he's not going to remove them. And they have been protected in phase 2. Right, so the first question is that sound in the sense of, am I sure that I'm not removing too many objects? And I think we have discussed it now that the invariant 2 makes sure that this is sound. The invariant 2 makes sure that everything that is a U is something that nobody else is interested in and I am not interested in. Is that safe in the sense of can I have data races? So here I am running through my heap and I am reading. Can it be that somebody else will be modifying the heap as I am doing it? What is the answer to this one? It's yes, but why is it yes? Type system. So we know that when we go and navigate in stage 2, the objects that are reachable from me, I am navigating only things that the type system allows me to read. So in particular, when I am in phase 2, I will stop here. I will not go and go from 3 and read 5. But when I am marking as R all local objects, then I don't need to go through the heap. I am just marking the objects, and I can keep the table of those objects locally to the actor. So there is no data race between, perhaps we should look at it again since we do have some time. So first mark all object as U. The actor keeps a local table for all the references that he's interested in. This table is not stored in the heap, it is stored in the actor. So this marking, although I have indicated it as if it was happening in the heap, it is happening in a local data structure of the actor. Then we find all the objects that are reachable from the current actor, and we mark them as R. So note that as soon as we hit tag, we don't navigate any further. And in particular, if this actor, while we are doing garbage collector, wanted to go in there and mutate and do whatever he wanted, then it would be fine. He would not be interfering with the garbage collection phase. Alpha 1 would not be interfering with the garbage collection phase of alpha 2. Then in the next phase, I go and mark as R all local objects that have got a reference count greater than 0. So even though this is not reachable for me, and it's not safe for me to be going in the heap and ticking boxes, all this ticking is happening locally within my own table, so I'm not interfering with any other actor. And then we go and we do the collection, which by invariant 2 we have said is dead anyway, so it's fine, and therefore the whole thing is safe. All right, and the last question is, can this be done in an efficient manner? One part of the efficiency is we are keeping those the necessary tables locally to the actor, which means that we don't need to load more data from memory. The other question is this navigation where we go through the objects and we scan them further. How much information does it need to have at runtime? Can it be done does it need to get information at runtime, or can it be somehow generated statically and therefore be more efficient? And the answer is the second, of course, since the whole point is about it being an efficient way of doing garbage collection. So every object has got, we can think that every class has got a scan method, and the scan method uses the static type of the fields in order to decide whether it should read the field or just give the identity of the field and finish. For instance, the scan method of the object 1, whatever the class is, will know I have got an isoreference, therefore I need to continue scanning here. The scan method at object 2 knows I have got 2 tag references, therefore I need to give the identity, the contents of my fields, but I am not allowed to continue scanning here, and I'm not allowed to continue scanning here. Yeah?
So you generate the code for the marking for each?
Yes, there is a scanning method for each of the classes. Yes. And then there are lots of clever tricks how to avoid things being recursive by pushing things in on the stack, but I'm not going to talk about them. So this is how it works at the high level. So that is the local object collection, and we owe it all to this invariant 2. This invariant 2 is super powerful and wonderful. So great, but then the question is, how do we make sure that the invariant 2 is preserved? And it follows from another 2 invariants. The first invariant says that if an object or an actor is reachable from another actor, then that actor has got a reference count greater than 0 for the object. So if I have an object that I can reach, it's not mine, it belongs to Juliana, then I also need to have a reference count greater than 0. Juliana needs to have a reference count greater than 0, and I have to have a reference count greater than 0. So that introduces the idea that Juliana and I need to have got some consistent view of the world. We don't have the same view of the world in our reference count, but they need to agree in some sense. And here is the magic formula that's going to follow us for the next half hour. It says the local reference count, the ORCA message count, plus the ORCA message count. So this is the view that the owner has of an object. This is to be the same as the global view, the view that all the other actors have, the global system. So the foreign reference count, I'll tell you what they are. So that's the global view. So the foreign reference count is the sum of the reference counts in all foreign actors, in all non-owning actors. And the application message count is the number of in-flight messages which talk about the particular object. So if there is an application message around that is going to use that object, we need to take account of it. If there is some foreign actor that is interested, by invariant 2, we need to take account of that too. And so this is the global view, this is the local view, and I'm going to give an example in order to explain it all again. So let's assume that we have got a runtime configuration as follows. So it's a simplified version of what we had earlier. We have 3 actors. There is a path from alpha 1 to 1, 2, and 3. From alpha 3 to 4 and 2, but then it stops, it cannot read that one, and here are the reference count. So the local reference count of 3. This is easy, it is the reference count of the owner. The owner of 3 is 2, so the local reference count is 4. The ORCA message count, which is the number, which is the sum of what is in the ORCA messages. Well, there is no ORCA message for 3. There is an ORCA message for 2, but that does not affect 3, so it's 0. The foreign reference count, this is the sum of the reference count of the foreign actors, the other actors. So it is 1 plus 2, which makes 3, and the application message count, let's have a look. There is a message that wants to read, that contains 4, and let's assume it does not pass it in a tag capability. So from 4, I can reach 2, but 3. And because 2 and 3 are owned by alpha 2, it's also alpha 2. And it is alpha 1 because 1 is owned by alpha 1. So now for these guys, for those that are owned by alpha 1, namely alpha 1 and by alpha 1, I have to increment. is are there data races? The third one is right. So when we do the sending, to send that sound? Yes. Is that safe? Yes. Is the point where my reference count is not high enough? I could go through a scenario, but please believe me. So what we should be Oops. So if and otherwise, what we need to say, I'm going to tell the owner, please make one by sending, we have left our own reference count the same and we have incremented that one. So that works, but we can be a little bit more proactive and we say rather than just ask for one extra reference count, we can ask for many. So we can ask for 256, and now we set our own reference count to 256. So again, we are rebalancing the invariance here. So now if we look at garbage collection, it's a little bit more work than we have said earlier. And here it is how it is updated. So we first mark all the objects from the reference count table and all the local objects as U, unreachable. Then we find all the objects that are reachable and mark them as R. So that's pretty much as we had before. We mark as our all local objects with reference count greater than 0. We collect everything that is unreachable and local. But for the others, which are unreachable and foreign, well, we are not interested in them anymore. So we give up our own reference count. So we remove the reference count and we send to the owner the message, I have given up this reference count. So we send a negative ORCA message to the owner. So for the particular case, all the objects from the reference count table and all local objects marked as U are those objects. So note that we don't mark as U6 since it is not in my own table. Then we find all the objects that are reachable from the current actor. There are not that many. We mark them as R. We mark as R everything that is local and has a reference count greater than 0. Okay. So now we can collect all local objects marked as U. So the local objects marked as U is 5. we collect it, we remove all memory of it, and now we have to do something about the remaining unreachable objects that do not belong to me. I cannot collect them because I don't know whether there are more actors interested in them, but what I have to do is I have to tell the owner, I'm not interested anymore, so we remove them from the reference count table and we send a negative ORCA message to the owner. Right, so what about cycles? Reference counts have got problems with cycles. What do we need to do anything now to extend the protocol so that it finds cycles across objects? So the answer is we don't need to do anything, because when there is a cycle, when each of if there's a cycle of unreachable objects, when the owner of each of these unreachable cycles does garbage collection, it will inform the other, the owners of the other objects in the cycle that they are not interested in that object anymore. And in the end, we will reach a point where the local reference counts for these objects will be 0. So if you consider the cycle that we have here between 3 and 4, when alpha 2 does garbage collection, it will not find 4. It will send a decrement message to alpha 1, so then they will be able to, sorry, when, yes, when alpha 2 does garbage collection, it will have had 3 in its reference count table. It will not find it when it does the local tracing. Then it will send an ORCA message to alpha 1, and alpha 1 will be able to remove 3. Yeah.
So I guess it's possible. So that means you can send and receive messages without allocating an object.
Yes, when you receive a message, you are passed references to objects, either val, tag, or ISO. In all these cases, you don't allocate any new object for that. They have already been allocated.
But also the act of receiving and sending, the implementation of receiving and sending, does not allocate the objects.
No, the implementation, I don't know. We need a data structure, of course, in order to keep the message. But when we receive a message, we don't do any copying.
Yeah, I was thinking, like, let's say there comes an increment message in.
Yeah.
And then to store the increment message, I might need to roll over the buffer. And so if I would rely on the garbage collector to allocate a bigger buffer, then I would have a problem because basically I would have to run my GC before the reference count, before I can process the reference count that I just received.
Are you saying what happens if there is too many increment messages so that the garbage collection gets overwhelmed by the number of increment messages which take storage?
No, I guess what I'm trying to say is it a problem when I have to do a garbage collection while receiving so I'm in the middle of receiving an increment message.
Garbage collection happens only between behaviors. It is not something that happens concurrently. Every actor is either executing a whole behavior and finishing or doing garbage collection. So it is not as interleaved as you are thinking about.
What happens if I run out of memory before I finish?
What happens if there are so many messages that I run out of memory?
No, what happens when I run out of memory before I finish the chunk of work? Like before I process one?
Yes, so if you have a behavior that allocates a lot of memory and which becomes inaccessible during the behavior, in the current implementation, in the current implementation of Orca, you will overflow because it is in the current implementation, the garbage collection happens only after the behaviors. You could extend Orca so that it does garbage collection during the behavior, and then you would need to also trace from the stack, and this is a little bit more cumbersome. You need to store more information, and that is why it is not done. Now you are saying, so this would be notionally very easy to implement. Now you are saying, what if I want to do garbage collection during these phases that I have described now, during the execution of the sending and during the execution of the receiving? Do you have an answer to that? So because we have got a lot of exciting stuff and there is half an hour, I have to rush. Sorry. Yeah? Local cycle within the actor. Yes, because there we are working with through scanning locally. So if there was, so for instance, if 4 had a reference to 7 and 7 had a reference to 4, they are both not reachable, so they are going to be removed. We don't need the reference count and all that mechanism in order to. So this is a mark and don't sweep, but the reference counts are there only in order to coordinate, to make sure that we are not removing something that other people are interested in.
But you have to zero before you zero before
Not the reference counts. The reference count that persist. This is a very global, very persistent invariant, and if I had the time to talk about the proof, it would be even funnier. What we mark and unmark is the reachability, the R and the U. Every time we run the garbage collection cycle, we first mark everything as U, and then we go and mark as R everything that we can reach.
So this is not reference counting as we are used to. It's completely different. Maybe reference counting is another mechanism.
It might be unusual today.
Okay, so I would like to talk to you about causality briefly, so and message delivery. So here we have got a scenario where we have got alpha 1 has got a reference to 7, 7 is owned by alpha 2. So the unluckily named reference count of alpha 1 for 7 is 1 and for alpha 2 is 1, 2. This is invariant 2. Then alpha 1 wants to send a message containing 7 to alpha 3. So by what we said now, earlier, he needs to set his own reference count to 256. He will send an Orca message to alpha 2 saying, set your reference count to 256. Then he will send the message with 7 to alpha 3. Alpha 3 will set its reference count when he receives it, he sends his reference count to 1. Then, in our scenario, alpha 3 drops the reference to 7, is not interested anymore. He runs a GC cycle, and therefore he needs to say to alpha 2, I'm not interested in 7 anymore. Dereference, take 1 reference off your reference count. So the problem is, what happens if this message should arrive before that message at alpha 2? So if that happened, it would be a total disaster, because then alpha 2 would remove the object, even though there is still somebody who has an interest in one, namely alpha 1. And the answer is causality, namely this one happens before that one, so it logically precedes, this one logically precedes this one, therefore this one logically precedes this one and will be delivered first. So I would like now to, last bit, I'm going to go very briefly through it. If you look at sending and receiving, they are complementary things. So we scan a data structure when we send it, and we scan it again when we receive it. And we do that, we also scan a data structure when we are doing GC. So that seems a little bit repetitive. Why do we need it so often? But it is necessary in case the data structure changes in the meantime. Even though this one and the one will be doing the opposites of each other, the data structure might change, and we need to keep track of that. But if we send a value, then the data structure will not change, and we have got a deep immutability. So I will be sending a value to somebody, I will be doing all the scanning. The next one receives it, he does the scanning again. Then he sends it, scans, then the next one receives, scans. So that's a bit boring. And there is an optimization. The actor scans a value argument only once upon, sorry, it should be saying send. And only the owning actor scans the owned parts for val arguments. So that reduces the amount of scanning tremendously. So I will let Juliana present our benchmark results.
So I only learned that I would present it yesterday, so I hope it's not messed up. Yeah, so, evaluating Orca and Pony has been one of the most challenging things that I've done in my PhD. When we were starting, I was naive enough to think that I would do this in 2 or 3 weeks. And since then, 2 years have passed, and I'm not sure that what we have is actually okay. So the bad news is that maybe it's not a good idea what I'm about to show you. That's the bad news. The good news is that you can tell me how to do better, and then I would be happy to improve it. Yeah, at some point. So there shouldn't be a to-do here, or whatever this is.
The same as above.
Okay. So yeah, designing what we wanted to show in our evaluation was a bit tricky. We have been working a lot on that. Albert has been working with us too. And there were a few challenges that we did not know how to overcome very well. One of them is, what do you use as a baseline, right? Which benchmarks do you use? So whenever you open a GC paper, it's usually for the JVM. And this means that you can just use the DACAPU benchmarks, and that's it. Then you can just compare with some other approach. And unfortunately, we didn't have this advantage, because Pony is a fairly new language. It has been around 2 years, something like that. So, and although there are already some applications, they are either not open source or they are small. Yeah, that was one of the problems. Another problem was with which languages do you compare, right? Because all languages have different semantics. So what is it fair and what is not? For example, when you run when you run something on the JVM, there is this notion of global heap. So when you do some evaluation, what you usually do is you set different heap sizes and you check the performance of the application for these different heap sizes. But in Pony, we don't have this notion of heap size. So these ownership boxes, it basically means that each actor has its own local heap. And yeah, therefore, it's just different semantics, basically. So what are we evaluating? So we wanted to compare scalability, footprints, responsiveness, and we wanted to run Pony without GC and with GC. So for the scalability, it's, as you can imagine, we just change the number of cores, we measure total execution time, we get an approximation of the time spent on garbage collection, on sending and receiving, and tracing upon sending and receiving. For footprint, we are reporting the maximum resident size, so the peak of memory usage during the application. Yeah, I don't need to explain what is a program without GC, it just crashes. And responsiveness is very similar to what Richard Jones presented the other day. If you remember, he had these results where he measures how long a server takes to reply. So I actually took some inspiration in one of his talks for this benchmark. So yeah. So because we didn't have good benchmarks, we had to write ourselves some small benchmarks. And the reason that they are small, it's really just because I need to finish my PhD at some point. So yeah, so this trees benchmark, it's basically the benchmark that Laurie was talking about yesterday from the computer language benchmark game. And the trees prime is just a variation where we have more threads more actors being spawned. If you ever looked at this code, it just uses 5 or 6 threads. And we have been running these benchmarks on a 64-core machine. So we really wanted many, many actors. We wanted really to stress the number of actors being created. So the rings benchmark and the mailbox are from the Sabine benchmarks and maybe the CAF benchmarks. Just benchmarks that send really many, many thousands or millions of messages. So we basically want to evaluate how fast message delivery is. Then the heavy ring, it's very similar to the rings, but we want to pass really large graphs. And the reason why we want to do this, it's because you might remember that there's lots of work on message sending and receiving, and we want to check how Orca behaves when you basically put the finger on where it hurts, right? So and for the server simulation, the last one, it's basically we have these clients sending in messages to the servers do some works on trees, and then send a reply back to the clients, and we measure how long it takes to reply. Yeah. So for the trees benchmark, for example, you can see the total execution time for 4 cores. I don't like this thing. You can see the total execution time for 4 cores, 8 cores, etc. till 64. But you can also see how long it takes on GC and how long it takes on pauses. So for example, the C4 runs on runs with, the code was written in Scala with Akka. So you can see that most of the GC work in C4, it's concurrent, there's only a very small pause, and that's how it is supposed to be. But there's no pauses in Pony or Erlang. Well, Pony, you already heard about it, but why you don't see a pause in Erlang? It's because Erlang, it's very similar to Pony. So each actor has its own heap, and the actor is responsible to collect its own garbage. So in that sense, it was, choosing Erlang, it was an easy choice because they are so similar in the garbage collection part. So, and we'll also see some mutated overhead. The mutated overhead in Pony, it's sending and receiving and tracing upon sending and receiving, and in Erlang, it's time spent on copying messages.
So Orca is Pony?
Say again?
Orca is Pony?
Yes, Orca is the garbage collector that runs on Pony, so ownership and reference count for actors. So in most plots, if I did a big zoom in, I would be able to see the mutated overhead, so how long it takes on tracing upon sending and receiving. But then the screen wouldn't be big enough, so. So as I said, the difference between these two benchmarks is just the number of actors spawned, and each actor is creating trees, binary trees of different sizes. So as we can see, Pony is scaling, it's behaving a bit better than Erlang and C4. And while you look at Erlang and you see lots of time on GC, it's also the mutator time that it's way worse. So this is something that we are kind of proud of, because this benchmark is actually locating many, many, many trees, some gigabytes of data, and it's becoming unreachable quite quickly. So it's quite cool to see that for a large amount of garbage, Orca is actually dealing quite well, although there's no pause for a behavior. So the reason to have the rings benchmark and the mailbox, it's not so much about garbage collection, it's more like to show off a bit of Pony and how fast it is to deliver messages. And we actually managed to get some really good performance. So a small note, in this benchmark, we deactivated actor collection because, as Sophia will explain, if there's some time in the end, Actor collection requires some cycle detection work, so we basically do not collect actors in any of the benchmarks. Yeah. So mailbox again, Erlang, which is supposed to be scalable, it's not scaling. But what I really like about this benchmark is, although these messages only send some numbers, there's some copying work in Erlang. Like there is this ping here where you can see that some copying or messaging. And you don't see anything in Orca because, I mean, it's just sending numbers, so there's no extra work required. And of course, we were not measuring mutator overhead in the C4 because it's quite tricky to measure, to measure the mutator overhead when you have barriers. So yeah, footprints. We are basically measuring the peak of memory usage. So Orca doesn't behave as well as C4, for example, for footprints. And the reason why this is happening, I believe, it's because with C4, you can just set a global heap. So you can set the maximum size of the global heap. So basically, the maximum peak, the maximum usage of memory cannot go above that limit. And in Pony, we don't have as much control. But it's still quite interesting to see that Pony is actually competitive with Erlang in 1, 2, 3, 4 cases, and it's way better in the other one. Yeah. So of course that we have run this with and without GC, and for benchmarks like the rings and the mailbox, when there's not that much data located, it's quite comparable. So you can see here that there is it's slightly slower. It's normal. You need to set up all this data structure for garbage collection, but it's not super slower, so it's okay. But the interesting bit is to look at the Node.gc, to look at the Node.gc version in benchmarks that locate lots of data and see that GC it's really important here, right? I mean, and for some, when I was running these benchmarks, I needed to use smaller inputs, so I needed to ask the benchmark to locate less data because it would just explode. So, and this was on a really big machine with 124. Albert, the machine is 100. Say again? Of memory. So it's So that was quite interesting to observe, but it's also quite expected because basically you are creating space for memory pressure, and it's. I've heard many people saying stuff like, when you want when you want high performance, you just switch off GC, or why would you worry with garbage collection in a high performance language? So because of this, because sometimes you really need to locate lots of data. So So for the responsiveness, this one it's what I said before. It's just you want to check how long the server takes to reply. And again, we have good results for Orca, but the reason why you see less outliers here, it's because Orca opts for many garbage collection cycles, but smaller ones. So if you have a small GC and there's no pause in the system, the server will be able to reply quite quickly. And this is only possible because we have this notion of local heaps. So each actor will clean after himself. So basically, we pay a bit on the footprint side, but then we can have really nice responsiveness times. So, we have a really small set of benchmarks, and usually Pony behaves better than AK and SIF and Erlang. And of course, this doesn't mean anything. Maybe you'll be able to write a benchmark where Pony is really bad. I'm not sure. This is an example. So this is a Pony in pain. We usually call it. And basically what we are doing is we are using this heavy ring where we are sending really large data structures to other actors. And you can see for binary trees of depth 16, so really, really large, Pony behaves really bad. And I could try with depth 20, but then it would crash, or I would just wait the whole day or something like that. And it took me quite some time to realize why this is happening. I mean, I had this idea of, okay, so there's some work on message sending and receiving. There's all this tracing happening, but why is it this exponential performance? It's really bad. And if you look at it, the time in scanning, this darker blue here, it's not that much, right? So, but still, why is this happening? So then we figure out that when you send a tree, you trace it, but you trace it in depth first order, and basically, yeah, with depth first order, but the tree was built with the breadth first order. So there's lots of cache misses, and this is really degrading the performance in this particular case. So of course it's one corner case, probably there are more, we don't know. But the good news, so when an animal is in pain, and Pony was in pain, we take them to the vet, right? And in this case, taking him to the vet was just using this optimization that Sophia was talking about, where you use the type system, or the guarantees given by the type system for an optimization. So basically, whenever you are passing a graph which is immutable with a val capability, you don't need to trace it. And I don't have the plot here, but it's basically as good as passing a number, right? You are not doing any tracing, you are just passing a reference. So it's like passing just a value. So yeah, and in that case, Pony will behave way better than the other ones. So that was it. If you have any feedback or any new ideas that you want to give me that might improve this evaluation, please let me know soonish, at some point before I submit my thesis. That would be awesome. But yeah, and of course that this doesn't say much. It's a really small set of benchmarks, but it says something.
So in the remaining time, I want to talk about the proof, and I want to talk about garbage collection for actors. So I'm going to whiz through the proof. The reason I'm going to talk about it is because you might have some ideas what we can do about it. So it's relatively easy to prove completeness. So you can prove that in any configuration, there is an execution that will eventually collect all the garbage. And we have also a nice proof of soundness for Orca. It's about 10 pages of LaTeX. So we have got it. But it's more complex than we would like it to be. Same story as I said yesterday, but for different reasons. And in particular, we don't apply this figment of atomicity that I spoke about yesterday. And we believe that we should be able to apply this figment of atomicity. So what is that figment of atomicity? When we think about the semantics of concurrent execution, we break it down into interleaved execution. So we have got these three actors that execute concurrently, and we think that this one executes for a little while, then this one, then this one, then this one back again, and so on and so on. So this is what the model says of the interleaved semantics. But we said that because we have got this atomicity, because we know that from the point of view of the actor, between the time he receives a message and he executes the method, the world has not changed. The programmer can think in those terms. He can think that my method, my behavior, this behavior will execute exclusively, atomically, until it terminates, and then this one, and then this one. So this makes reasoning easier. So how wonderful if we could do that also in our proof. Let's now think about what we need to prove. We have got, for example, here the case where we are sending. We have the invariant for, and the invariant for says, for all objects, the view of the owner agrees with the view of the world of the object. Nice. Okay, so now let's think that we are executing this body. We reach this point, invariant for holds. We collect all the objects that are reachable, and then for each of them we do this. And here we are incrementing our reference count. So we have broken the invariant for the particular object for which we incremented the reference count. Then we increment the reference count for another object. Then we have broken their invariant, and so on and so on. And here we break the invariant, and this is visible outside the object, outside the actor, because we have put something in the message queue, and it is now, the change is visible to all over. It is visible to the actor in whose queue we have got this ORCA message. And at the end, when we send the message, we re-establish the invariant. So we would like to and when we started thinking about it, we would like to think about it atomically, but actually it is not correct to think about it atomically, because there are all these effects that break the invariant that is supposed to hold all over the system and upon which the other actors are depending. So what we have is that the execution of the behavior breaks the invariance at different granularity at different points. And in the interleaved semantics, there is no point in an execution where we know that all the behaviors have finished, because they are like this. And actually, this invariant 4, as is stated, does not need to ever hold in the system. So what do? We introduce co-state. We introduce even more variables that allow us to talk about the invariant 4. This works. It is fiddly. It does not reflect this figment of atomicity. We have totally given it up now. We require extra invariants, because we need now to say when do the ghost variables agree with actual variables in the system. And we still need to argue with this interleaved semantics. So it is all works, but it's a tour de force. So what we would like to have, and we have been discussing it for a while, is we would like to be able to go into the nice world of atomicity, make our proof, and then know that if some conditions hold for the system, it will also apply for the interleaved world. So this is an open question. If you are interested, please discuss with us. Termination. Okay, so a pony program terminates when all the actors have terminated, and an actor terminates when it is idle. It has an empty message queue, and all actors that have pointers to it are idle and have empty message queues. How long do I have, Laurie?
Just 10 minutes.
Okay, thank you. Right, so we say that an actor is dead if it is blocked, that it is idle and and it has got no pending messages, and all actors which may reach it are blocked. And now we have got the garbage collection protocol for actors, which is called MAC. We didn't have Juliana to give us a nice name for it at the time. So how do we detect the dead actors? Remember that we have got this nice invariant from before that says if anybody has a stake in an object, then the owner will have a positive reference count. And if an actor is reachable, then the foreign actor has got a reference count greater than 0, and this consistent view. And with all these properties, we can determine when do we have a dead cycle, when do we have a cycle of actors which are all blocked and only point to each other, because this is now the challenge. I said that detecting cycles of objects is no problem in ORCA, but now in MAC it is a problem. There is no actor above the actors that goes and finds when they are dead. So we need to design a new protocol. So if we have a set of objects that point to each other, and the local reference count of each of them is the sum of the reference counts of all the others, and they're all blocked, then we know that all those actors are dead and we can remove them. So here is an example of a dead cycle, because the reference counts, the sum of the foreign reference count is the same as the local reference count for each of them. So here he has got a reference count of 2, and those 2 has got a reference count of 1 each. And there are no pending messages, they are idle, and therefore there is a dead cycle. So that's perfect. That's very, very nice. But the problem is who will detect the dead cycle? Because what I am talking about here is a very transient property. All the reference counts change all the time. So an actor could be blocked, but then it can wake up, or it can decrement reference counts, and so on. So we would need ideally to be able to take a snapshot of the system globally and determine whether something is, whether the things are in a dead cycle, but there is no possibility to take a snapshot of the system. So who will detect the dead cycle? There is a dedicated cycle detector, but then we have got the problem that we're talking about a global property, and this property relies on information that changes. So the first version of the MAC protocol says, before blocking, you tell the cycle detector, you send him a message that is called, sorry for the idle there, it says, I have blocked. So you send your identity and you send the reference count for all the other actors. When you unblock, you tell the cycle detector that you have unblocked, and the cycle detector keeps track of information. So here is such an example of the first version. All the actors are blocked. Then the cycle detector receives information from alpha 1, from alpha 2, from alpha 3. Now he has got enough information and he has found the cycle. He kills them all happy. But what happens if this actor blocks, then he unblocks, and he sends the cycle detector a message that he has unblocked, but the cycle detector does not receive it on time, and he kills the actor. Or what happened if here alpha 2, after becoming idle, receives an ORCA message? Then the information about the reference count in alpha 2 is outdated, and the cycle detector would take a decision based on outdated information. So messaging of the actor paradigm to the rescue. So we update the protocol. So it's pretty much as it was before. When you are idle, you send a message that you are blocked. When you unblock, you send a message. Also, when you receive an ORCA message, you tell the cycle detector that you unblock. Then the cycle detector keeps track of all the information, detects a cycle. When he finds a perceived cycle, now he does not take action. He starts a conf-ack cycle. So he tells all the actors, he gives a token to this perceived cycle and asks all the actors that he thinks are in that cycle, please confirm. So he sends them confirm requests. If he receives an unblock message, then he destroyed the cycle, have responded with an acknowledgement, then the cycle is we have spent quite some time thinking of the actor who gave the acknowledgement at the time where he sent the block is the same as the state at the time when the cycle detector perceived the cycle. Yeah? Okay, so I'm not going to make a drawing. I'm going to say two things I was extremely annoyed that here we need the concept of time. But then I spoke with other people who have done proofs about garbage detectors, garbage collections, and they said, yes, the concept of time is necessary. The other point I'm going to make is when Sylvan came up with this idea, he had a totally different reason for why the system was sound. And I have tried to prove what he told me at the time. And then when I came up with this one, he was surprised, and now none of us can remember what his original idea was. So it is nice to make proofs because they give you better understanding in the end. So as I said, there is a couple of things that I'm interested in working on, and Sylvan has got a long list of things, and Tobias. Here are some. There is going to be one more talk on Pony at Carry On in Barcelona, and that is the end of the discussion of garbage collection from me today. Thank you. Okay, I think there was a lot of discussion during, so thank you. Yeah, thank you.